Hello everyone, and thank you for joining me today for the introduction of your virtual lecture course, Nuclear Materials. So this course is designed principally for materials scientists and engineering graduates and undergraduates interested in the many material science and metallurgy challenges present within the nuclear industry. Many of you will have had little to no prior education with respect to nuclear energy, and so this course should give you a number of fundamentals relevant across the wide variety of disciplines that you'll encounter within the nuclear sector. And for those of you taking this course as part of the Master's Programme in Nuclear Energy here at Cambridge, I strongly recommend that you first review my introductory lectures on material science for engineers, which you'll find in the NE3 module repository, as that will provide the fundamentals of crystallography, mechanical behaviour and microstructural evolution, all of which are necessary for you to follow this course. But for those of you taking Part 3 Material Science, you'll have already covered those fundamentals, and so it's clearly unnecessary for you to review those introductory lectures. So provided you'll feel well equipped enough to tackle the course, I hope it provides an enjoyable I hope it proves an enjoyable and interesting one. The nuclear industry is a really exciting sector to work in, pushing the boundaries of science with all the complexity and challenge you could wish for during any career you intend to pursue. One of the most rewarding aspects of nuclear energy for me was the opportunity to work with peers from a diverse range of engineering, science and technology disciplines, and collaborate on problems that require really a broad range of expertise in order to solve them. And there are not that many industries where you get to be involved with such a diverse array of disciplines. And material science is just one of those disciplines, but it's an important one. The decisions that we make with regards to the materials we use in, for example, reactor design, have great performance, reliability and safety implications. And at the heart of this is material degradation. And that's the life-limiting factor of a nuclear power plant. In almost every case, the primary obstacles in bringing the next generation nuclear power plants to fruition are materials challenges, be it due to the high temperatures involved, the corrosive environments present, or, as I'll show you, the effects of radiation. And there's much opportunity to make your mark in the nuclear industry as a material scientist. Now, evidently, if these material challenges are so numerous, it's going to be almost impossible for me to cover all of those in one lecture course. And so we'll focus specifically on the most prevalent. And they are the effects of radiation on structural materials and the reactor core. Because, as we'll see, radiation can change the shape of materials, causing volume increases of some tens of %. It can increase the hardness of materials fivefold, reduce their ductility, toughness, and it'll accelerate general corrosion, or even introduce new corrosion phenomena that are only seen under radiation. So the set of lecture notes to accompany this course are quite comprehensive. They contain everything you may be examined upon. However, as I said, nuclear materials is a pretty extensive topic, too large to cover in one course. So should you like to understand things in a little bit more depth, I've suggested, as you can see on your notes, a number of useful books that will carry you comfortably into a career within the nuclear industry. If I had to choose one companion text for this course specifically, I'd probably recommend Murty and Charrett's An Introduction to Nuclear Materials, which I made sure is available within both the engineering and the materials department libraries. So you shouldn't have any trouble finding those. So if you take a look at your notes, which I've got on the screen here, I will have those on the screen throughout the lecture course. So you may follow me as I go, and you'll see that the course is split across 7 main topics. The first will be covered in our first 2 lectures, and that's an introduction to the fundamentals of radiation and nuclear reactions, such as nuclear fission and fusion, the basic materials considerations involved in the respective technologies, and the most prevalent reactor designs, both in operation and those being proposed for an implementation in the near future. Our second and last chapter on the more fundamental aspects of nuclear materials will be on radiation damage. And those two chapters will provide you all the necessary information to then look at the specific components that we'll cover in sections 3 to 6. So nuclear fuels, their cladding, moderators and control rods. And then lastly, we will look at corrosion-specific aspects of those structural components, most notably stress corrosion cracking. So with so much to do, we better get stuck in with some of the fundamentals of nuclear energy. Well, to understand nuclear reactions, we've got to first familiarise ourselves with the standard notation. The first of which is how we present a nuclide, and that's how I've identified here. So as shown, we've got A, which represents the mass number, i.e. the number of protons and neutrons, Z, or Z for our North American brethren, being the atomic number, normally placed in subscript to the left-hand side, and N, the neutron number, i.e. the number of neutrons, with the sum of the neutron number and atomic number equaling the mass number, A. However, to make things more difficult, there are various notations used, such as the hyphen notation, where the number after the hyphen is the mass number, and that's what I've shown you here for uranium-235, an isotope which you will become very familiar with by the end of the course. And these nuclei, such as uranium, each nuclei have an associated binding energy. This is the first main fundamental that we need to think about. And that binding energy, that's an energy that's released in its entirety when a nucleus is assembled from its individual nucleons, your protons and your neutrons. So it's the energy released when those are combined and assembled into that single nucleus. And the greater the energy released, the lower the potential energy of the nucleus. And this energy is also equivalent to the energy required to split the nucleus into its component nucleons, not only the energy released when you assemble them, but the energy required to split them into its individual component nucleons. And so that means that the higher the binding energy, the more stable the nucleus. Okay? And so that leads us to really quite a key point in our harnessing of this nuclear energy, as should a nucleus be converted to another nucleus of higher binding energy, for example via fission or fusion, the difference in the total binding energies of those nuclei that we had then is released as kinetic energy. Kinetic energy of the resulting particles and any gamma ray that may be emitted at the same time. And that might be confusing at the moment, but I'll describe in detail later about gamma rays. So the key thing is that we need to take advantage of the difference in the total binding energy of the nuclei to grab that kinetic energy and produce power. So should we desire to harness that nuclear energy, we've got to maximize the binding energies between the target nuclide, i.e. the nuclide we start with, and the product nuclide, or nuclei, that we end up with. And that's what this figure here shows. It's the binding energy as a function of atomic mass. And as you can see, for small atomic masses, to the left-hand side, such as for hydrogen, if you increase the atomic mass, that leads to a huge increase in the binding energy per nucleon, which is the y-axis. And it's far greater jump than if you were to, say, reduce the atomic mass of a heavy nuclide on this side, such as uranium. Eventually all reaching the maximum binding energy per nuclide for our most stable nucleus, which is iron 56, right at the top of the graph there. So if you capture this energy released as kinetic energy and use it to produce electricity, well, what you have is a nuclear power plant. But as you know, there are two types of nuclear power, fission and fusion. And those two differences are on the different sides of the graph. If you harness the combining or fusing reactions resulting in the climb up the left-hand side of the curve, you've got a fusion plant. If you harness the fissioning or splitting reactions to the right-hand side, we have a fission plant. And as we will see, those two methods of capturing nuclear energy require very different methods. So, what can cause a nucleus to change its stability and release some of this energy? Well, to understand this, let's first learn what's meant by radioactive decay. And there are three types of radiation to consider here. There's alpha radiation, beta radiation, and gamma radiation. There are three types. So let's start with alpha. Well, alpha radiation is the emission of an alpha particle, which is essentially a helium nucleus made of 2 protons and 2 neutrons. Most alpha particles are produced through the decay of heavier nuclei, such as uranium-238, another isotope of uranium. We've mentioned 235. And that's what I show in the reaction here for uranium-238. So if you look at this, it's where uranium-238 undergoes alpha decay, so its mass decreases by 4, and its atomic number decreases by 2. And that means that it results in producing thorium-234, accompanied by that emitted alpha particle. And what we have there, as I mentioned, is a change from one chemical element or isotope to another. And that phenomenon is defined as transmutation. Transmutation is the change of one chemical isotope to another. And I will define that, I will term that as transmutation. So here, alpha decay has led to uranium-238 transmuting to the more stable thorium-234, with thorium-234 having a higher binding energy per nucleon, so it's more stable. Another method of stabilization is beta decay, and beta decay results in the production of beta particles, which are high energy, high speed electrons or positrons emitted as a result of the decay. So, say a nucleus has an excess of neutrons, more than it would like to have. It wants to stabilize. So it may undergo beta minus decay, which is shown here. And that's the changing of a neutron into a proton and electron, and an antineutrino, as I show here for carbon-14 in your notes there. So for the carbon-14, as it undergoes beta minus decay, it results in nitrogen-14. So the mass number doesn't change, only the neutron number does. Similarly, beta plus decay can occur, and that's where a proton is converted into a neutron rather than a neutron into a proton. So you get a proton converted into a neutron and a positron and a neutrino. And both of those reactions stabilize the nuclei, depending on what it's got in excess of. Okay, so last but not least is gamma radiation, which I mentioned before with the splitting of uranium-235. And gamma radiation, as most of you probably know, is high frequency and therefore high energy electromagnetic radiation. And gamma decay occurs following from alpha or beta decay, where the daughter or product nuclei is left in an excited state, i.e. with an excess of energy. And so in order to move to a lower energy state, in order for that nucleus to move to a lower energy state, it spits out a gamma ray and loses some of that excess energy. And all of these types of radioactive decay can be modelled based upon something called the half-life. So what is the half-life? Well, radioactive isotopes are subject to exponential decay, i.e. the number of nuclei of radioactive atoms decreases at a rate proportional to its current value, exponential decay. And I've shown that mathematically in your notes here, where n brackets t is the number of undecayed atoms after a time t, and lambda is the decay constant. Should you find the solution to that differential equation, you get the following, where N0, or N0 for our Americans, is the initial number of radioactive atoms, and tau is the mean lifetime of the radioactive atom in question. And the half-life is simply related by 1 over tau. So what actually is the half-life? Well, the half-life is defined as the length of time after which there is 50% chance that an atom has undergone some form of nuclear decay. Or as I like to think of it, the total time it takes for half the radioactive atoms to have decayed. So if the half-life is 2,000 years, there will be half as many radioactive atoms in 2,000 years. And putting this into the equation, what I've done is replaced T with the half-life. You can resolve the equation and relate it to tau, and find that tau is around 1.44 times the half-life. Okay? And that half-life varies significantly. It's not just one number. It varies significantly across different isotopes, from 10 to the minus 24 to 10 to the 30 seconds. So a huge change across the half-lives. And there's databases of experimentally quantified half-lives available online for you to use in any calculations you choose. Databases which, presented in graphical form, show what I've got here. And here what we see is we have different isotopes plotted to show the half-life and the nuclear decay type. And they're differentiated by the colour. Half-life on one graph, decay type on the other. So let's take an example. So you can see, for example, that very heavy nuclei tend to undergo alpha decay, or fission. Fission is the green one. And looking at the right-hand side graph, should a nucleus deviate from the stable ratio of protons to neutrons along that line, it results in a very low half-life, because as it proceeds to stabilize itself, it decays. So it wants to have a particular ratio of protons to neutrons, and so it will start to decay to stabilize itself. Okay, and that sort of concludes the first bit of our lecture, where we've gone over the real key fundamentals, as we will continue to do so now, but looking at neutrons and their reactions. So they're the very basic notations and some of the terminology that I'm going to be using for the rest of the course. What we're going to look at now is neutrons, their reactions, how we classify those, and a number of reactor designs that take advantage of these reactions. I should mention that if you have any questions, feel free to use the Q&A function on the module page, or the commenting page on the video. Otherwise, I will see you for part 2.